It is easy to think that quantum mechanics is just a theory about tiny particles and nothing more. But what if I told you that quantum mechanics may predict that you can never truly experience your own death? Welcome to one of the strangest ideas in physics, quantum immortality. Our intuition tells us that the world is predictable. If you throw a ball, it follows a definite path. But quantum theory tells us something very different. Everything we see around us is described at the deepest level by waves of probability. An elementary particle does not simply travel along one path. In quantum mechanics, it can be described as taking many possible paths at once. And despite all the paradoxes of quantum theory, despite how incompatible it feels with our everyday view of the world, it has one undeniable advantage. It works. Its predictions are among the most precise in all of science. Quantum electrodynamics, for example, predicts the magnetic properties of the electron with extreme accuracy. That is why physicists take quantum mechanics seriously, even when its meaning feels almost impossible to accept. Take an electron. It does not have to be in a clear state of spin up or spin down. Instead, it can be in a superposition, meaning both states at the same time. Only when we measure it does it seem as if the electron chooses one definite spin. The easiest way to understand this is to remember the famous Double-Slit Experiment. Imagine a barrier with two narrow slits next to each other. Behind it, we place a screen. Now we send electrons toward the barrier. What should we see on the screen? Common sense says we should see two bright bands, one behind each slit. That is what we would expect if electrons were ordinary little particles. But something completely different happens. On the screen, we see several alternating bright and dark bands. This is called interference. It is how waves behave, not particles. Even more surprisingly, this pattern appears even if electrons are fired one by one. Each individual electron seems to pass through both slits at the same time and create a wave pattern. And now comes the strangest part. If we put a detector near one of the slits to find out which slit the electron passes through, the magic disappears. The interference pattern vanishes, and the screen shows two blurred bands, just like we would expect from ordinary particles. So when we do not look, the electron behaves like a wave, but when we measure it, it behaves like a particle. This strange duality is not limited to electrons, neutrons, atoms, and even entire molecules. In 2019, physicists from the University of Vienna and their collaborators observed interference in molecules made of about 2,000 atoms. These were already very large objects by quantum standards. They passed those molecules through a special grating with many slits. If the molecules were ordinary particles, they would simply pass through some slits and form a blurred spot. Instead, an interference pattern appeared. The molecules behaved like waves. And this leads to an uncomfortable conclusion. The boundary between the quantum world of waves and the classical world of particles may be conditional. Maybe there is no fundamental border at all. Everything in our world obeys the laws of quantum mechanics, but the larger an object becomes, the harder it is to notice its wave-like properties. Large objects, including ourselves, constantly interact with the environment: air, light, heat, other objects. This interaction works like continuous measurement. It forces objects to behave like ordinary classical things. But if we could completely isolate ourselves from every external influence, then in principle, even a human body would have wave properties and could be described as being in a state of superposition. The consequences of the double-slit experiment may be among the deepest in all of physics. They overturn our intuitive picture of the world and show clearly that the universe is not what it seems. If this feels confusing, do not worry. You are in good company. Richard Feynman, one of the creators of quantum electrodynamics, famously said that nobody really understands quantum mechanics. For about a century, scientists have argued about what quantum mechanics tells us about reality, but they agree on one thing. Before measurement, particles are described by waves. This is called the wave function. In 1926, Erwin Schrödinger formulated an equation that described the motion of these particle waves. When he applied it to hydrogen, where one electron is bound to one proton, the results matched experiment beautifully. More than that, the behavior of chemical elements and the bonds between atoms can be explained using this same framework. In a certain sense, everything around us can be described through solutions of the Schrödinger equation: atoms, molecules, chemical bonds, and therefore the matter out of which the visible universe is made. But then a simple question appears. How does a wave of probability suddenly become one definite result? For a long time, the main explanation was the Copenhagen interpretation. According to this view, a particle exists in superposition, in all possible states at once, until it is observed. When observation happens, the superposition collapses and the particle appears in one definite place.
The probability of where we find it is given by Born's rule. Roughly speaking, we square the wave function. This model fits experiments, but it does not explain why collapse happens. Schrödinger invented a famous thought experiment to show the problem. Imagine placing a cat inside a sealed box. Inside the box, there is a radioactive atom, a Geiger counter, and a device that releases poison if the atom decays. If the atom decays, the cat dies. If it does not decay, the cat lives. The question is, before we open the box, is the cat alive or dead? Because the decay of the atom is a quantum event, the atom has to be described by quantum mechanics. Before measurement, it is in a combination of two states, decayed and not decayed. Since the atom is connected to the detector, and the detector is connected to the poison, and the poison is connected to the cat, the whole system seems to become a combination of two waves.
One wave describes a living cat. The other describes a dead cat. The cat is not simply alive or dead. It is, according to the mathematical description, a combination of both states. The only way to say whether the cat is alive or dead is to open the box and perform a measurement. Then, the wave function collapses into one outcome, a living cat or a dead cat. In other words, observation seems to determine existence. For Einstein, this was absurd. He disliked the idea that reality depends on observation. He once asked a version of the question, does the moon exist only when someone looks at it? In 1957, physicist Hugh Everett proposed a completely different view of quantum mechanics. He said that the wave function never collapses. Instead, all possible outcomes happen at once, but in different, separate realities. This idea became known as the many worlds interpretation. For a long time, most physicists ignored it, but today it is taken seriously by some well-known scientists, including Sean Carroll, David Deutsch, and Max Tegmark. According to this interpretation, our universe consists of countless parallel worlds. They are almost identical, but they differ in the details of quantum events. When it seems that a particle chooses one state after measurement, it has not really chosen. It exists in both states, but in different branches of reality. These branches are not somewhere far away. They exist in the same physical universe, in the same space, but they no longer interact with each other, except in special cases where quantum interference is preserved. If the many worlds interpretation is correct, then every time an event with an uncertain quantum outcome happens, reality branches.
Imagine you are in a dangerous accident and you have a 50% chance of survival. According to the many worlds interpretation, the universe splits into two branches. In one, you die. In the other, you survive. But here is the important part. According to some physicists and philosophers, your consciousness can only continue in branches where you remain alive.
You can never become aware of yourself as dead because the dead do not have experiences. So from your subjective point of view, no matter how dangerous the situation is, perhaps you will always find yourself in the branch where you survived by some extraordinary coincidence. Even if, objectively, the odds of survival approach zero, there may always be at least one branch where you continue to exist, and that is the branch in which your consciousness continues. This is the basic idea of quantum immortality.
Max Tegmark spent a lot of time thinking about whether there could be an experiment that would convince a person that Everett's parallel universes are real. In his book, Our Mathematical Universe, he described the following thought experiment. And no, under no circumstances should anyone try this. Imagine a device like quantum Russian roulette. For example, a quantum machine gun. Every second, it fires with a probability of 50%. The trigger is controlled by a quantum measurement. If parallel universes are not real, then you hear 1 or 2 clicks, then the gun fires, and that is the end. The chance of surviving for a full minute is less than 1 in a quintillion. But if Everett's parallel universes are real, then after each measurement, there are 2 worlds. In one, you are alive. In the other, you are dead. But consciousness can exist only in the living version. So from your own point of view, you hear only clicks.
After 10 clicks, Tegmark argued, you would personally have very strong evidence against wave function collapse, but that evidence would belong only to you. In countless other worlds, people would simply see you die. Hugh Everett himself did not write scientific papers about quantum immortality, but his biographers have reported that he believed in a kind of immortality that followed logically from his theory. He thought consciousness would always continue along a path that does not end in death. But this does not mean that you would be forever young, healthy, and happy. It would mean something darker. You would continue in worlds where life continues at any cost, even if everything is terrible. That is why the idea sounds insane. But it follows from the internal logic of one of the most discussed interpretations of quantum theory. Not all physicists accept it, many reject it. But the argument is strange enough that we have to look carefully at where it comes from.
Max Tegmark begins Our Mathematical Universe with a memory from his youth. As a schoolboy, he was riding his bicycle on an empty road, approaching an intersection. A moment later, he thought he died. He hit the brakes, but it was too late. Headlights, a radiator grill, a massive truck. Time slowed down. His life flashed before his eyes. His last thought was that he hoped it was only a nightmare, but he knew it was real. Reality is not always what it seems. This is true of trucks, and it is true of the world around us. Physicists know that solid steel is almost entirely empty space. Atomic nuclei contain almost all the mass of atoms, but occupy only a tiny fraction of their volume. This near vacuum feels solid because of electromagnetic forces holding atoms in place. And subatomic particles can be in several places at the same time. That is the essence of quantum physics. So if our bodies are made of these particles, can we ourselves be in 2 places at once?
Tegmark wondered whether a single atom in his brain could have affected his decision at the intersection. Maybe one calcium atom entering one synapse in his prefrontal cortex helped trigger a neuron, which triggered a chain of neural activity which produced the thought, "Look right." If that atom had been in 2 slightly different positions at once, then half a second later, his eyes might have been looking in 2 directions. A few seconds later, his bicycle might have been in 2 places. And a little later, he might have been both alive and dead. If he exists in 2 different places in 2 parallel universes, then one version of him survives. And if we apply the same reasoning to every possible way he could die in the future, it seems that there may always be at least one parallel universe where he never dies.
Since his consciousness exists only where he is alive, does that mean he is subjectively immortal? And if yes, would the same be true for you? If you open a classical textbook on quantum mechanics, you may see something like this. Atoms can be in several places at once, but large objects cannot. But this sounds strange. We are made of atoms. If atoms can be in different places, why can't we? The answer is decoherence. Our universe is like a giant construction set. Everything in it, from mountains and water to stars and your smartphone, is built from the same basic ingredients: atoms. Atoms themselves are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. Electrons, as far as current experiments show, appear to be elementary. CERN's Standard Model describes these elementary particles and the forces acting between them.
But for quantum immortality, the important point is this: all matter is quantum matter. Light is quantum too. In 1905, Einstein showed that light comes in particles called photons. Earlier, Maxwell had shown that light is an electromagnetic wave. Today, we know that radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all parts of the electromagnetic spectrum. NASA explains this spectrum as one continuous family of electromagnetic radiation. Einstein understood that the energy of a photon equals its frequency multiplied by Planck's constant. That is why high-frequency light carries more energy than low-frequency light. This explained the photoelectric effect, for which Einstein received the Nobel Prize. So matter and light both have quantum properties. But what laws do these particles obey? The answer is the Schrödinger equation.
There is good news and bad news. The good news is that we have an equation. The bad news is that it does not predict exactly what each particle will do. It predicts how probabilities evolve. And nearly a century after its discovery, physicists still debate what this means. Before quantum mechanics, it was natural to imagine the atom like a miniature solar system. Electrons orbit the nucleus, like planets orbit the sun. But classical physics leads to a disaster. A moving electron should radiate energy and spiral into the nucleus almost immediately. Hydrogen atoms should collapse. They do not. They have existed for billions of years. So it became clear that the microscopic world follows different rules.
In 1913, Niels Bohr proposed that electrons could occupy only special orbits. When an electron jumped from a higher orbit to a lower one, it emitted a photon. When it absorbed the right photon, it moved upward. This explained the spectral lines of hydrogen and helped Bohr win the Nobel Prize. But Bohr's model did not fully explain more complex atoms. Louis de Broglie went further. He proposed that electrons are waves. Just as sound waves in a flute can have only certain notes, electron waves in an atom can exist only in certain allowed states. This helped explain why atoms do not collapse. Werner Heisenberg then developed the uncertainty principle. We cannot know both the exact position and exact momentum of a particle at the same time. The more tightly we try to localize an electron, the more uncertain its motion becomes. Schrödinger then wrote the wave equation for these particle waves, and modern physics opened.
The wave function does not describe a particle as a little dot moving along a fixed path. It describes a cloud of possibilities. In a hydrogen atom, the electron does not orbit the nucleus like a planet. It exists around the nucleus as a probability cloud. Some places are more likely than others. These are not ordinary waves, like waves on water. In a water wave, water moves. In a quantum wave, what waves is the probability of finding a particle in one place or another. This is quantum superposition, the ability of a system to exist in several possible states at once. But then the puzzle returns. Why do we never see a cat in two places at once? Why do we never see a human body both alive and dead? Schrödinger's cat was designed to push this problem into the open. There are three key ingredients in the thought experiment: superposition, entanglement, and measurement.
Superposition means that a quantum object can be in more than one state at once. The double-slit experiment demonstrates this clearly. The second ingredient is entanglement. Imagine two particles interacting and then flying apart. After the interaction, they may no longer have separate wave functions. Instead, they are described by one shared quantum state. If we measure one, we instantly know something about the other. The 2022 Nobel Prize in Physics honored experiments with entangled photons, Bell inequalities, and quantum information. So entanglement is not speculation, it is a tested part of modern physics. Now comes measurement.
Is it not strange that a quantum system should obey one rule when nobody looks and another rule when someone measures it? If we look deeper, measurement is just interaction between quantum systems. Electrons interact with photons. Photons interact with detectors. Detectors interact with air, light, and eventually with our eyes and brains. We already know how quantum systems interact. Their wave functions evolve according to the Schrödinger equation. So why should measurement need a special rule? If we remove the special collapse rule from Schrödinger's cat, then the superposition of the radioactive atom becomes entangled with the detector. The detector becomes entangled with the cat, and when we open the box, we become entangled with the entire system. No collapse is needed. Instead, there are two versions of us. One sees the living cat, the other sees the dead cat.
These two versions do not meet. They do not communicate. Each version experiences one definite outcome. This is the many worlds interpretation. But where do these worlds come from? They come from decoherence. Particles in the environment, air molecules, photons, and other disturbances interact with the system and carry information away. Once the environment has learned which branch is which, the branches stop interfering with one another. A macroscopic object can remain in a visible superposition only if information about its state stays secret from the rest of the universe. But large objects are terrible at keeping secrets. A single photon bouncing off an object can reveal where it is. Air molecules do this constantly.
That is why we do not see large objects in two places at once. It is not because quantum mechanics stops working. It is because large objects are almost impossible to isolate. No human observer is required. Consciousness is not required. The environment itself performs the measurement. This is also why quantum computers are so difficult to build. They must preserve quantum information long enough to compute. But decoherence constantly destroys delicate superpositions. Modern quantum computing is essentially a battle against the environment. In 2000, Roger Penrose and others discussed the possibility that the brain might involve quantum effects in a deep way. Tegmark examined this mathematically. The brain is warm, wet, and full of moving ions and molecules. A neuron firing involves huge numbers of charged particles. If the brain were trying to maintain quantum superpositions for ordinary thought, decoherence would destroy them extremely fast. This does not mean the brain violates quantum mechanics. It means the brain is probably not a useful quantum computer in the ordinary technical sense. Now we return to quantum immortality. The quantum suicide thought experiment is very similar to Schrödinger's cat. You simply place the observer inside the box. Only the person whose life depends on the quantum event could, in principle, distinguish the interpretations from a first-person point of view. According to the Copenhagen interpretation, after the first trial, the chance of survival is 50%. After each next trial, it is cut in half. After enough trials, survival becomes practically impossible. But in the many worlds interpretation, after every trial, reality branches. In one version, the experimenter dies. In the other, the experimenter survives. And because only a living observer can be aware of what is happening, the observer always finds himself in a branch where he survived.
That is quantum immortality. However, Max Tegmark emphasized three important conditions. First, the source of randomness must be quantum, not classical. Otherwise, you do not get the clean superposition of alive and dead. Second, death must happen faster than you can become aware of the result. Otherwise, you do not get a clean division between a living observer and no observer. You get a suffering observer. Third, the experiment must kill you with certainty in one branch, not merely injure you.
In 2001, philosopher David Lewis gave a lecture with the striking title, "How Many Lives Has Schrödinger's Cat?" It was his first and last lecture on quantum mechanics. A few months later, Lewis died. In that lecture, later published after his death, he discussed a frightening idea. If the many worlds interpretation is true, then an observer should always find himself in branches where he survives. And since every cause of death is ultimately grounded in quantum physics, the observer might expect subjective survival through any danger. But this guaranteed survival does not mean health or happiness. Lewis compared it to the ancient myth of Tithonus: endless aging, endless decline, always almost dead, but never quite dead.
Tegmark did not fully accept this dark conclusion. The problem is that real death almost never satisfies the three required conditions. Death is usually not a binary event. It is a gradual process of consciousness fading. Neurons do not all shut down at once. Self-awareness becomes blurred and dissolves. There is no sharp line between life and death, only a continuum of states. This smooth transition is one reason quantum immortality is probably impossible in the real world. Yes, in many worlds, there may be branches where you survive almost any dangerous situation, but the measure or weight of those branches becomes smaller and smaller. In the mathematics of quantum mechanics, not every branch has the same importance. The Born rule gives different weights to different outcomes.
Imagine that you are a wave function. At the beginning, your existence is concentrated in many normal branches. But with each nearly impossible survival, the branch in which you continue becomes thinner, smaller, less typical. It may exist, but that does not mean it should be treated as a promise of immortality. This is why many physicists reject quantum immortality, even if they take many worlds seriously. The many worlds interpretation may say that all outcomes occur, but it does not say you should ignore probability. It does not make danger safe. It does not make death a scientific illusion. From the outside, you die.
From the outside, you die. From the inside, the argument depends on controversial assumptions about consciousness, identity, probability, and what counts as you after branching. If reality branches, which future observer is really you? All of them? One of them? If there are many future versions with your memories, is there a single thread of consciousness moving forward, or are there simply many successors? Physics gives us wave functions, amplitudes, entanglement, and decoherence. It does not automatically answer the philosophical question of personal identity. So quantum immortality is not a proven prediction. It is a thought experiment, a disturbing one, a powerful one, but still a thought experiment. What makes it valuable is not that it promises eternal life. It forces us to confront what quantum mechanics may be saying about reality.
The Double-Slit Experiment shows that particles do not follow one definite classical path. Schrödinger's cat shows that quantum measurement becomes deeply strange when amplified to everyday objects. Decoherence explains why we do not see cats, people, and planets in obvious superpositions. Everett's many worlds interpretation says the wave function never collapses. Instead, reality branches. And quantum immortality asks one final question. If one branch contains your death and another contains your survival, which branch can you ever experience? The responsible answer is this. No interpretation of quantum mechanics gives you a reason to take real risks. Quantum immortality is not a life hack. It is not evidence that you are physically indestructible, and it is not something anyone should ever try to test.
But as an idea, It is one of the strangest in science because it connects the most personal fact of human existence, death, with the most impersonal machinery of physics, wave functions, measurement, probability, and the structure of reality itself. Maybe the wave function collapses. Maybe all branches are real. Maybe the final interpretation of quantum mechanics is something we have not yet understood. But one thing is certain. The universe is not built to satisfy human intuition. It follows rules that are mathematical, precise, and deeply alien. Quantum immortality may not mean that you will live forever.
But it shows that the question, what does it mean to exist, is not only philosophy. At the deepest level, it may also be physics.